Hi, this is Logan, and today I'm going to be presenting on challenge assessment number 3. So the problem that we're going to be looking at today has to do with a spherical communication satellite with a given diameter, solar absorptivity, emissivity, incident radiation, thermal conductivity, and midpoint temperature. So we're supposed to find the surface temperature and the heat generation rate. What we want is a lower surface temperature here because cryogenic propellants, they must be stored at a lower temperature or else they evaporate and you can't move the satellite. So first, I started with some hand calculations using first the conduction equation. I simplified that because it is a steady state problem with a constant k value and approximated it as a one-dimensional sphere. My two boundary conditions were symmetry and a constant k value. For symmetry and a constant center temperature. I then integrated that twice to solve for the temperature distribution equation. Over here, I then plugged in the boundary conditions to simplify that temperature distribution equation. Then I used Q dot radiation and Q dot solar to find Q triple prime, and then I plugged that back in to find the surface temperature. And I found that as you increase the radius, the temperature of the outer surface also decreases. So the larger the satellite, basically, the lower the edge temperature, which is what we want. I then adjusted the K value, or the thermal conductivity, with that gray line being the value with the lowest K value and also the lowest surface temperature. So when we want this lower surface temperature, we want to choose a material with a lower K value to bring that down. I then took a look at the midpoint temperature and found that that is where that line crosses the y-axis. So the lower the midpoint temperature, the lower the eventual edge temperature will be. And lastly, I adjusted the heat generation rate just to see what that would do. But I found that if you increase that heat generation rate, that surface temperature will go down and would be ideal. So the ideal satellite would have a lower K value, a higher heat generation rate, and a lower midpoint temp, so as to not evaporate the cryogenic propellants.